One of the most important applications of integration is figuring out volumes of rotated solids. And just like when we find the area under a curve by adding up rectangles, we're going to find the volume of a rotated solid by adding up cylinders. So to start off, remember from geometry that the volume of a cylinder is pi r squared, the radius of the base, times the height of the cylinder. And most of the time, we're going to be looking at cylinders that are turned on their side, okay? So your height is going to be going this way, and your radius is going to be going that way, and your axis of rotation is going right through the middle of it. So what if we have the curve y equals 2 root x? So it looks roughly like this. From 0 to 4. So this point is at 4 comma 2 square root of 4, which would be 2 times 2, which is 4, 4 comma 4. Okay. And what happens if we rotate this around the x-axis? Well, if we rotate this around the x-axis, it's going to go like this, isn't it? And all this whole curve is going to follow it, going around like that, and we're going to get a bullet shape. Now, let's think of a representative disk. So let's say we've got one disk right here, okay? Here's the height of that disk. There's the radius of that disk. The height is dx. It's a little bit of thickness in the x direction. And the radius is how far up you're going to the y coordinate of that point at x. So your radius is y. So I'm going to use GeoGebra to demonstrate what's happening. So here's our little representative rectangle. If I rotate around the x-axis, look. It goes like that, right? Okay. And there's your radius. And notice that your height is dx. Okay. Here's a disk. Now, what happens if I go from 0 to 4? Well, with one disk, that's not very good. But what if I do 4 disks, 5 disks? What if I do an infinite number of disks? Then I get the exact volume. Okay, and when we do an infinite number of disks, dx goes to 0. So that means we're going to use an integral to find the volume. So the volume of one disk, which I'll call dv, is going to be pi times the radius squared of the disk times the height. Well, we just said the radius is the y coordinate at this point right here where the disk is. So it's going to be pi y squared. And we said that the height of this cylinder or disk is dx. Well, what is y? Y is 2 root x. So this becomes pi 2 times the square root of x squared dx, which is, now when I square this, I'm going to get 4 pi, the square root of x squared is x, dx. That's the volume of one disk. So how many disks do we want to add up to get the whole volume from 0 to 4? We want to add up an infinite number. So that volume is going to be, I'm going to put the 4 pi in front. 4 pi integral, we're going to start our disks at 4. We're going to start them at 0, and we're going to end them at 4. X dx, which is 4 pi x squared over 2 dx. Whoop, don't need the dx anymore, do we? Because we've already taken the antiderivative. From 0 to 4. And 4 over 2 is 2. So I get 2 pi, plug in the 4, minus 2 pi, plug in the 0. And we get 2 pi times 16, which is 32 pi. So the volume of this entire bullet-shaped solid is 32 pi cubic units. Okay, let's do another example. So let's say we're going to take this curve, y equals x squared minus 4x. Now, this curve looks like this. It's a parabola, and it intercepts the x-axis at 0, 0, and 4, 0. And we're going to rotate this thing around the x-axis like that. So I've done this in GeoGebra just to give you a demonstration, and here's what happens when we rotate it. Can you see that? And I'm going to swing this around so you can take a look at it. So the y-axis is green, the x-axis is red, and the z-axis is blue. Okay, you don't have to worry about the z-axis, but this is kind of a yo-yo shaped thing, isn't it? And if I only rotate it halfway around, you can see how it opens up. There's it's rotating around the x-axis. Okay? So that's what the shape looks like. Okay, so let me finish drawing that right here. I'm going to erase this. So this thing is going like this, and a representative disk would be going like this. There's the front of it, and there's the back of it. Okay, now there's our height, dx. This is a random point on the curve, x comma y. Here's our radius, and our radius is y. So what's the volume of that red disk? The volume of just the disk is pi times the radius squared times the height. Y in this case is x squared minus 4x. So that's pi x squared minus 4x squared dx. Okay, so we're starting our disks at 0, 0, and we're stopping our disks at 4, 0. So that means that the volume of the total object is the integral from 0 to 4 of pi x squared minus 4x squared dx. And I will move that pi in front. And we could multiply that out and take the antiderivative of each individual term, but let's use our calculator, okay? So I'm going to go to alpha F2, and I want to do function integration, which is number 4. And remember, you can also hit your math button and then number 9. We're going to go from 0 to 4, and I'm going to go x squared minus 4x, close parentheses for that, square it, and that's in terms of x, enter. And if I want to get a fraction, I can hit math, convert to fraction, and it's 512 over 15 pi. Let's do one more example, and this time instead of rotating around the x-axis, we're going to rotate a function around the y-axis. Okay, so here's the question. What's the volume of the solid when y equals sine x? So sine x from 0 to pi over 2. So sine x is going to go from 0 to pi over 2. It's going to look like that. This point here is at pi over 2 comma 1. And we're going to rotate this thing around the y-axis. Okay, so let's see what that would look like. Okay, watch as I rotate this sine function around the y-axis. Okay, so we get a shape that looks like a whirlpool or something, or a tornado, right? So we're going to get the volume of that whole thing right there. Okay, now here's the difference. Instead of my disks going like this, now my disks are going to be going like this. So that means that my height now is dy, and my radius is going to be x. So if I draw this out, so it's going out like this, it's going around the y-axis. Here's a representative disk. Here's our point, x comma y. then our height is dy, and our radius right there is x, because going from the y-axis out to the point x comma y. So the volume of our disk is pi, and my radius is x, so r squared is x squared, and my height is dy. Now I have dy, which means I have to write this in terms of y, not x. Well, if y equals the sine of x, then the inverse sine of y is x. So I'm going to go pi times the inverse sine of x squared, no, inverse sine of y, inverse sine of y squared dy. All right, now here's nothing to watch out for. Since I'm talking about doing everything in terms of y, for my limits on my integral, I have to go from the starting y value, which is 0, to the top y value, which is 1. Okay, so I'm going to go pi inverse sine of y squared dy from 0 to 1. Now you're definitely going to need to use a calculator for this. And make sure that you are in radian mode when you're doing this, okay? All right, so here we go. I'm going to go math 9, 0 to 1, parentheses, inverse sine alpha y, close parentheses for the inverse sine, close parentheses for the function, square it, and then put alpha y. Enter. We get 0.4674. And let me make sure that you can see that. Yep, that's our answer. 0.4674, not y. Sorry about that. Pi.